This lecture is on windowing and grid techniques. Essentially, we want to discuss the consequences of having a discrete grid and using finite differences and some tricks and tips we can use to overcome that. We will review the last lecture, and then the remaining part of this lecture is divided into three groups. Windowing, and this answers the question of we would like to run our simulation for an infinite number of time iterations. What if we don't? So how to minimize the consequences of limiting the duration of the simulation. That brings us into windowing. Then we want to discuss more building devices on a grid. And we're fitting this to a Cartesian grid, which is inherently square. So if we have some kind of rounded object, its round edge will be discretized in some way, kind of look like a staircase. And so what are some ways we can handle that? Then we also have to think about the fact that we're building devices on a Yee grid where the fields are staggered, and so we are defining the, for example, epsilon xx, epsilon yy, and epsilon zz. We are defining those permittivity tensor elements at different points. Epsilon xx exists at the same point as ex, epsilon yy at the same points as ey, and epsilon zz at the same points as ez. So suddenly they're existing at different points. We may have a curved boundary that slices through the middle of a cell, and it gets crazy. What's a simple way we can get through this? And that's where this 2x grid technique comes in. First, we'll review last lecture. Last lecture, we did a formulation of a two-dimensional finite difference time domain code without yet the complications of a perfectly matched layer. That's coming. Another thing we did different from the one-dimensional formulation is that we normalized the electric field quantities instead of the magnetic field. And so Maxwell's equations looked a little bit different. And the last thing we did differently is we did not substitute in one of the constitution relations. So in fact, in this formulation, we proceeded with two curl equations, and we left d equals epsilon e. We left that constitutive relation out of the curl equations, and we'll handle that separately. So in a way, we have a three-step update. Rather than go EH, we're updating d from h, updating e from d, and then updating h from e. And then that cycle repeats itself. So here's our revised block diagram. Update h from e, update d from h, update e from d. And then that repeats, and it just keeps repeating. So no more EH. Now it's HDE, 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 HDE. We began deriving our update equations by taking our three remaining of Maxwell's equations, and I guess I'm being lazy calling those Maxwell's equations. One of them has the B equals mu h constitutive relation substituted into it, so it's not purely Maxwell's equations anymore, but we have Maxwell's equations. We expanded those, and now we have a set of 9 coupled partial differential equations. We approximated those with finite differences. We then discussed how we're always modeling a three-dimensional device. Even if our model is two-dimensional or one-dimensional, we're always modeling a three-dimensional device. And we discussed going from a three-dimensional device to 2 dimensions. And we chose a uniform direction to be z. We crossed off all the z derivatives in Maxwell's equations, and we saw that Maxwell's equations then decoupled into 2 distinct modes. One we called the EZ mode, and the other we called the HZ mode. We then revised our FDTD algorithm, in this case specific to the EZ mode. We're calculating now for an update, we're calculating our curl part of that first, and then doing the update equation and using that curl in there. So to update the H field, we really have 2 curl terms. And this is also where our boundary conditions ended up. Given these 2 curl terms, we then update our H fields. We then calculate the curl term, to update the D field. We incorporate the source and then update the E field. And then this process repeats itself and we iterate over time. That brings us to this lecture. And yes, this word windowing is intentionally blurred because, in fact, that's what happens to your spectra when you limit the time that you limit the time of a simulation. So let's think about our finite difference time domain simulation. We have a device, our grid. We have a place where we're injecting the source. We have a place where we're recording the reflected fields, a place where we're recording transmitted fields. At the point where we're injecting a source, this is what our source might look like as a function of time over the course of the simulation. Well, that pulse will hit this interface, it will reflect, some of it will transmit, it'll start bouncing back and forth, and every time it does that, it transmits some and reflects some. And if we look at our recorded reflection spectrum, we see that. We see these pulses coming back. And they get smaller and smaller. We can't see them out here, but they are there. And on the transmitted side, we also see this pulse, and we see the ringing within the device, and that keeps going, even though magnitude-wise, we no longer see them out here. So this is what comes out of an ideal finite difference time domain simulation. But we can't run our simulation forever. Suppose we limit that. Suppose we only run our simulation for a time ts, and we just end it here. Essentially what we're doing is setting everything outside of here to 0 because we're not counting it in any of our spectra or anything. So we're just assuming it's 0 if we do that. So what are the consequences of that? We've calculated the stepped parameter with some specific number. No matter how big we make that, in principle, it will never be long enough. It needs to run to infinity to represent physical reality. So the question is, how long does that need to be that it's good enough for us? So let's back up and let's pretend right now we're not talking about finite difference time domain. We're just looking at the impulse response. And I just made something up here. In fact, I started in the frequency domain and made up some strangely shaped transfer function. And if we look at this in the time domain, this is what the impulse response would look like. So let's say that's the impulse response that we would record from our finite difference time domain simulation. And if we Fourier transform that, we get our ideal spectra. This is what we would get if we ran our finite difference time domain simulation out to infinity. But of course we can't do that. So we need to limit it in time because we can't run our simulation. So essentially what that's doing in the time domain, we have the window of our simulation. It has to start at some point and it has to end at some point. We know we initialize everything to 0, so everything will be 0 before the simulation starts. It'll do whatever it does in the simulation, and it probably hasn't ended yet, but we will end our simulation, so we're not counting any of the stuff in our Fourier transforms or anything like that. So essentially, in terms of the spectral responses that we're calculating, we are setting everything outside of this to 0. So it's just like we took our infinite impulse response and multiplied it by this square window that encloses the duration of our simulation. So this product now looks like this. So all of the information we want to learn about our model has to come from this spectra, which is not really the spectra of the infinite time domain simulation, if you will. It's 0 out here. And clearly there's information that we're missing. So what is the consequence of that? Let's think about this. We have two time domain functions. We have our infinite impulse response. That's what we would get if we really did have a finite difference time domain simulation that simulated out to infinity time. But we multiply it by a window function. So we have this multiplication. Remember, if we have a multiplication of two functions and then Fourier transform that, that's just like we Fourier transforms the two functions independently and then convolved them in the frequency domain. So here we have the infinite impulse response. That's the actual physical answer we're after. We only run our simulation over some finite period of time. That's our window. Well, if we're doing a point-by-point multiplication in time here and then Fourier transform to get to the frequency response, that's just like we Fourier transformed our impulse response. So this is the actual physical frequency response of the device. But we're convolving it by the Fourier transform of the window. Our window is a square function, so this comes out looking like some kind of sinc function. We are convolving the actual physical spectrum of the device with a sinc function, so it's being blurred. The actual spectrum that the physical device would have is being blurred by this sinc function. So clearly we want that sinc function to go 0 in duration, but that requires this window goes out to infinity, which is not physical reality. Okay, so here is our window function, and we actually Fourier transformed it, and we get this sinc-looking function. So that's our window function in the frequency domain. Window function in the time domain, a finite duration simulation, our window function in the frequency domain. So we're taking this little sinc function thing, and we will convolve the actual physical spectrum with that, and so it gets blurred. So let's do that. In the red here, I'm showing the actual physical frequency response that our model should calculate if we ran it out to infinite time, but it's being convolved by this little window function. So it's being blurred by this function. So in other words, every point gets blurred according to this profile. When we do that, here's what we get. So in other words, if we ran our finite difference time domain simulation but ended it at a certain number of steps according to this window function, this is the spectral response that we would calculate from our device. This is physically what we would measure in the lab if we built it. This is what our model would predict. Clearly there's some similarities there, but they're different enough for us to be concerned and think about this in a bit more detail. So here's the trend. If we have a really long simulation, we're really not clipping this very severely. We're convolving with a very narrow function, almost an impulse, and we get out almost the exact spectral response of the physical device. If we limit our window by a little bit, now we're convolving with something that's a little bit wider, that blurring's a bit more severe, and it really doesn't resemble the original spectra that much. Well, if we limit that time window even more, we're convolving it with a function that's even wider, it's even more severe blurring, and we get a frequency response now that we really can barely recognize. So clearly, in order for our spectra to resemble reality at all, there's a certain minimum amount of time that we need to run our simulation in order to get what we're expecting, or what we should get. So how do we do this? Well, first of all, we know from the Nyquist sampling theorem that given some time step in our model, that sets a limit on the absolute maximum frequency that we can resolve. And we talked a little bit about this before as well. Then, the number of steps really sets our frequency resolution. How finely can we resolve frequencies? And why is this? Because if we limit our number of steps, our spectra gets blurred. So we can actually go calculate points that are more finely spaced than this, but there won't be added information simply because those points that we've calculated very close are blurred into each other, and each frequency point really contains a blurring or an average of the response over all of the adjacent frequencies. So the time steps sets the upper frequency limit. The number of steps tells us how finely we can resolve frequency due to this windowing function. So how do we calculate the number of steps? Well, if we know our time step and we know how finely we want to resolve frequency, we calculate this little quantity and round to an integer, and we run our simulation for at least that many steps. So that ensures we'll get the frequency resolution that we need. Now, for devices that have very sharp spectral features, we need very high frequency resolution. So in other words, this little delta F will be a very small number. And since we're saying 1 divided by a very small number, delta T will also be very small. This ends up being a very large number. And so we need a lot of steps. So anytime we know we're going to have sharp spectral features, which usually happens with highly resonant devices, we know we need a lot of number of steps. Here we talked about it in the context of windowing and blurring our spectrum. Physically, we can also say we have power stuck in the highly resonant device, and that needs to leave so we can record it as either transmitted or reflected. So both of these stories are saying the same thing, that we need to run our simulation for at least a certain number of steps to get all the power out, to resolve our frequencies. Okay, on to dielectric smoothing. Here we have a device. We're going to put it on our Yee grid, which is Cartesian, inherently Cartesian. So we need to make even round things look like squares. And there's some implications of that. There's also some things we can do about that to improve things. So real quick, what is dielectric smoothing? And we can explain this in terms of our one-dimensional model. Let's say we've calculated a grid, and we want to fill it in with some dielectric bar, if you will. And so, but this dielectric bar is not an exact integer number of cells. For whatever reason, we couldn't do that or didn't do that. And so it slices partially through one of the cells. Well, let's focus in on this one cell where that's partially cutting through. And it actually looks like this. So this is one cell on our Yee grid. However, the physical device ends somewhere intermediate. And let's say that's about 30% through the cell. So that means 30% of the cell has a dielectric constant of 6. 70% of the cell has a dielectric constant of 1 because it's air. So what we do is we take some kind of weighted average and we get this average dielectric constant. So in this case, what we would do is in this one cell, we would just assign it a dielectric constant of 2.5. So now we've essentially used a blurring, if you will, to help us resolve this structure that ended up slicing partway through a Yee grid cell. So in fact, this gives us a pretty accurate simulation. This is more accurate than just rounding this and either making it a little bit too short or much too long. This improved things considerably. And we can actually get away with a coarser grid by doing things like this. So the reasons for doing this, and in 2 dimensions we're going to have rounded, curved contours that slice through a whole bunch of cells, and we would have to go to a ridiculously high number of cells for round structures to really look round. That's not practical. So if we smooth them, that is doing something called improving the rate of convergence, meaning we can use a much more coarse grid than we would need otherwise. So this makes our simulations run faster than they would and take up less memory, which is all very good. So here's how it works. Let's say our physical device is a cylinder, or in this case a circle in the in a 2-dimensional cross section. Well, we calculate our grid and we put a circle on here. So at the resolution of our grid, it has to look like this, and we have this staircasing happening, which is not good. We're physically changing the device. These should be round edges, but they're not. So in fact, this is the device we're actually modeling. Clearly, the device we're modeling is not the physical device. Hopefully close enough, but it's not. And so that can change our answer, sometimes pretty significantly. Well, here's another thing we could do. We could build our circle on our grid and then do some kind of blurring operation on it. Now the device we're modeling does look round, but this outer part is a little bit graded, which can tend to weaken reflections off of it, which really isn't physical. So we don't want to do a lot of blurring here. But it's definitely closer. We're doing better. Not perfect, but better. So here's how we can do the smoothing. We start off with our physical device. What I like to do then, we calculate our grid, and this is maybe, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. This is 9 cells wide, probably 9 cells tall. Instead, let's calculate a grid that's maybe 100 by 100 cells, a very, very high resolution grid. And we'll build our circle on it. So clearly this looks a lot more like a circle than it would on this very low resolution grid. Then what I like to do on this really high resolution grid is fill in a block that's the same physical size as one cell from the original grid. And I will Fourier transform both of those, multiply them, and then inverse Fourier transform. So really what I've done is convolve these two. I've blurred this cylinder according to this function, 1 pixel on the low-res grid, and I get out this blurred sort of representation of the circle. So here's the blurred version of the circle overlaid onto our 1x grid. Then what I'll do is I'll go one cell at a time, and I'll look at the middle value on that really high resolution grid, grab it off of that, and fill in the cell. And so when I do that, here's what I end up with. And this is a really clever way of doing the averaging. So I'm building the device on a very high resolution grid, blurring it over the width of 1 pixel on the low X grid. That does the blurring, and then I just go grab the middle value from each of those cells from that high resolution grid and fill it into the low resolution grid. Then I have a nice smooth structure. And this is pretty easy to do. It's only a few lines of code in MATLAB. We can get fancier about this. What I've just showed you works very well, but we can do better. So this next bit of conversation is not something I'm going to hold you to in this class. You could choose to do it as a project or just experiment with it, but certainly not necessary, because what I'm going to show you will require us to actually have the full anisotropic tensor for the permittivity and permeability. So I'll talk you through it, but we're not necessarily going to do that in this class. So what we have in Maxwell's equations is the product of two functions. We have the permittivity times the electric field E, and there's also a permeability times the magnetic field H. And that's where our whole boundary problem is focused. So A in this case might be permittivity, B might be the electric field, and F is just the product of the two. So let's forget about Maxwell's equations temporarily and just think we have the product of two functions. And convergence is slow. We'd like to improve this. Well, if we took A, which has a discontinuity, which is why the convergence is slower to begin with, we have some kind of discontinuity, we've already sort of shown if we just blur that, we can improve convergence. So we fixed this. When one of the functions, A or B, has a discontinuity, we can fix that by blurring it. Or improve it. I shouldn't say fix it, we just improve it. Now let's say both A and B are both discontinuous. That's even worse. That convergence will be really slow. However, let's say that while A and B are both discontinuous, let's say the product of the two is still continuous. Well, what we could do then is on the right-hand side where we had an A times B, we'll bring A over to the left-hand side. So now what we have is just one discontinuous function, which we can fix with blurring. Over here we have a discontinuous function, but times a continuous function. That goes back to our first case, if you will. And we can fix this simply by blurring now the reciprocal of A. So we blur the reciprocal of A, and now let's bring this reciprocal back over here because we originally had F equals A times B. And so we have this sort of double reciprocal thing happening. We took the reciprocal of A, blurred that reciprocal, and then took the reciprocal again, which in fact is different than just blurring A. It may seem like this is the same, but in fact we get slightly different numbers. And this is how we fix the case when both A and B have a discontinuity at the same point, but their product is still continuous. So here's the summary. If A and B are both continuous, no problems. We don't have to do anything. When A has a discontinuity, we'll blur it. We'll smooth it. If A and B are both discontinuous, but their product is still continuous, we'll do a sort of a double reciprocal thing. We'll take the reciprocal of A, we'll blur the reciprocal, and then take the reciprocal again. So it's kind of like we're back to A, but we did a different blurring, and we end up with different numbers, slightly different numbers than we would have seen just blurring A. And in fact, this helps convergence a lot. Now we have to go back to the fields to understand the context and why this works. So we've pulled off our constitutive relation, D equals epsilon E. And it's this epsilon E is where the troubles occur, because we can have material interfaces causing our epsilon to be discontinuous. And we know we also have boundary conditions and things, so our electric field is not perfectly continuous. So what we'll end up doing is we'll decompose our field into parallel and tangential components. And if we remember from our physical boundary conditions, the tangential component of the electric field E is continuous across the interface, which means there's no problems with that one. The perpendicular component, or the normal component, is discontinuous across the interface. What saves us here, though, is that the product of permittivity times the normal component of the electric field, that product is continuous across the interface, so that's fixable. Let's think about how we'll do that. So let's think about epsilon times E. Well, one thing we can do is we can separate E into parallel and perpendicular components. So if we add those together, we just get the total overall field E. Then what we can do is we can multiply this side out. We just have an epsilon times the parallel component, and then the same epsilon times the perpendicular component. But now we have an epsilon multiplying the parallel component and the perpendicular component. This gives us the opportunity to treat those two epsilons differently. So this epsilon we'll write as epsilon parallel, and this epsilon we'll write as epsilon perpendicular, because we could blur them differently, or now we have an opportunity to do something differently. Well, let's think about what we do. For the parallel component, or the tangential component of the electric field, that's continuous across the interface. So we have one discontinuity times something that's continuous. So all we do is blur this. Over here we have the normal component of E. Remember, the normal component of E is discontinuous across the interface. Since we're talking about an interface, the permittivity is also discontinuous. However, the boundary condition, the physical boundary condition, says that the product of these two is continuous across the interface, which really helps things, which means we do the double reciprocal thing to this epsilon perpendicular. So we'll take the reciprocal of the permittivity, we'll blur that reciprocal function, and then we take the reciprocal again. So it's kind of like we just blurred epsilon, however, we get slightly different numbers doing it this way. So we start off with the same epsilon for parallel and perpendicular, but we've blurred them differently. And we apply just the direct blurring to the tangential component of E, and the perpendicular blurring to the perpendicular component of E. At this point, we really only have a partial solution, because we have to break the electric field up into perpendicular and parallel components, and it's not immediately known what is perpendicular and parallel to an interface. So is there a way that we can tie all this together in kind of one final simple equation of how we blur our epsilon? And so that's what's going to happen now. So we start off with D equals epsilon E. And since we're talking about perpendicular and parallel components, by necessity our permittivity needs to be a tensor here. So this is what our tensor looks like. It has 9 elements, and we need to figure out some simple rule to fill that in. Even though we start off with something isotropic, once we blur according to this formulation, suddenly it becomes anisotropic. So we've divided our electric field into parallel and perpendicular components. How on earth do we know that? So I have 2 examples down here. One's sort of a horseshoe-shaped dielectric object, and another's kind of a double cylindrical object. These are 2 dimensions, and the idea extends to 3 dimensions. But we need to create some kind of vector field that's always pointing normal to the interfaces. That'll tell us what direction is normal to the interface in order to get the perpendicular component of the electric field, and then the remainder part of that has to be the tangential component. So somehow we need this normal vector field, and so we'll go with that. There's a lot behind calculating this normal vector field. There's some good literature out there. I referred to one paper here. Suffice to say, that isn't easy and that is not trivial, but I don't want to sidetrack us on that. A lot of times maybe if our geometry is simple, it's just a square or circle, then we'll analytically know that. Determining that for an arbitrary case is a bit more difficult. So moving forward, we'll pretend that somehow we know that. And so our normal vector function will simply be this. So now we need expressions for the perpendicular and for the tangential components based on this normal vector field. So let's think about the perpendicular component first. If we take the dot product of that normal component field with the electric field, what we essentially get is just the scalar component of the electric field normal to the interface. Well, we want this to be a vector. We have to give it a direction, so we also multiply by that normal vector again. So that gives us the component of E normal to the interface and also gives it a direction normal to the interface. So the parallel component is then simply the total electric field minus what we've calculated up here. So now we have an expression for it. So given that normal vector field, we are able to decompose our electric field into the normal tangential components, or parallel and perpendicular as we're saying them here. So in terms of matrices, here's what the perpendicular component looks like. We want the x, y, and z components of the perpendicular vector. And so we fill in the math as we've derived it. Then what we can do is we can pull the e's out to a column vector over here, and we're left with a big square matrix that uses the components of that normal vector field that we can multiply by the electric field to get just the normal components. So we've pulled it into one little matrix for doing that. So we'll call this matrix a big N with a hat on it. So that's the matrix that we can multiply by a column vector of our electric fields to get another column vector of just the perpendicular fields. So using that notation now, our normal or perpendicular component is just this matrix N times E. That means our parallel component is just the identity matrix minus that normal vector matrix times E. So we can use this matrix N to calculate both the perpendicular and parallel components. Okay, back to the beginning. We have D equals epsilon E, but we separated E into parallel and perpendicular components. We then multiplied this out, and we had an epsilon times the parallel E plus an epsilon times the perpendicular E. This gave us an opportunity to treat these differently, and as we saw, we have to blur them differently. The epsilon multiplying the parallel component or the tangential component of E, we just blur. Over here, we'll take the reciprocal of epsilon, blur the reciprocal, and then take the reciprocal of that blurred function. So we can treat these separately, and after we do the blurring, I have these little double brackets here showing that we've blurred this and blurred this, and here's how we do it back to our blurring notation. But essentially these double square brackets mean this is a blurred function. So the one we assign to the tangential component of E, we're just blurring. The one that we assign to the perpendicular component of E, we do the double reciprocal type of blurring. Okay, so here we have this blurred function on the tangential component of E and the double reciprocal blurred function multiplying the normal component of E. So, but we have matrix expressions now describing how we do this, which we can substitute in. We have this function multiplying E, which gives us the parallel component, and we have just the matrix N multiplying E to give us the perpendicular component. And we do a little bit of algebra to factor out the E, and we end up here. Remember, the original constitutive relation was D equals epsilon times E. So what is in curly brackets here now is a modified version of epsilon. So our smooth epsilon is now the standard blurred epsilon times this matrix plus the double reciprocal blurred epsilon times this matrix. Doing a little bit more algebra to simplify down, we end up here. So if somehow we can calculate the normal vector field and construct this matrix and then do two different flavors of blurring, one just the standard blur, the other the double reciprocal blur, we can multiply all this together and get an anisotropic permittivity. which is a blurred version. So here's the summary of what you do. It all comes from the fact that d equals epsilon e. We will first blur our epsilon two different ways. We will then calculate our normal vector field and form this matrix. And once we have that, we can tie it all together to get a blurred and anisotropic permittivity. And if we needed to, we could also do the same thing to the permeability. Same equations, just we're pulling out a d and an e for b and h, and pulling out permittivity for the permeability. Otherwise, it stays the same. So let's see what this actually looks like when we do this anisotropic blurring. So here, we're using a 25 by 25 grid, and we're building a device with a dielectric constant of 5, and it's in air. And it's just a cylinder. And we blur it according to this recipe we just laid out. Well, what we see, going down the diagonal, are functions that look very, very similar. We see we have these two off-diagonal terms where we have rather significant numbers in these two terms, making it truly anisotropic. We can also look at these two and these two, which looks crazy, but if we look at the magnitude, they're way down there. So what we're looking at is just numerical noise. Essentially, these two elements and these two elements in the tensor are zeros. So we have a function going down the center diagonal, and then we also have these two off diagonals. So that's in the XY cross-section of a fully three-dimensional device. And we can look at another cross-section. And here, this is the XZ cross-section. We still have the same things going down the diagonal. These two are in the numerical noise, so they're really just zeros. These two are in the numerical noise, so they're really zeros. And we have these two again. Let's try to visualize it another way in actual full 3 dimensions to get an idea of what this looks like. And here's our dielectric sphere, if you will. So we see we have a bunch of big numbers in there. They get smaller and smaller, so we can visualize our blurring this way. And we also see that these off-diagonal terms contain some numbers only at the boundaries. So, and when we look at these crossing through certain planes, that's what we saw on the previous slide. So this is what it looks like when we get this anisotropic blurring going. Now, this is rather sophisticated. There's issues modeling anisotropic structures, and it still turns out we can do really good if we just simply blur the permittivity and not worry anything about it being anisotropic. We can still improve the convergence. I just wanted you to see this. So a real simple simulation. We have slabs of two materials. Depending how we choose our grid resolution, let's just say we can't simultaneously represent both of those with an exact integer number of cells. Although in this case, since one layer is exactly half of the other, we probably could pick a grid resolution intelligently to do it. But let's just say we can't. And we simulate these. We actually do see quite a difference in the spectra between the two. And comparing them to a higher resolution grid, we see about an order of magnitude improvement for a given resolution. So this does help us a lot. So some final comments here. Even if the original device is made of isotropic materials, if we blur this exactly how it needs to be done, we end up with something that's anisotropic. And probably the most difficult component of that is calculating this normal vector field, which we really didn't even get into. So that can be difficult. But even if we ignore the anisotropy and just do simple blurring on our isotropic structure, we can still improve convergence. I just wanted you to see that there's really more to the story. The other thing to mention, if we think about what the E mode is, we're confined to a two-dimensional plane, and the electric field is out of that plane. That really means the electric field is always tangential to any interface. So that means just ordinary blurring will work. Likewise, in the H mode, we can just do ordinary blurring of the permeability. But for the permittivity, the H mode, we still can just blur sort of normally and improve our convergence. But that really strictly requires an anisotropic smoothing of the permittivity, because the electric field's in the plane. So the moral here is we're just going to go with standard smoothing, not worry about anything being anisotropic. We'll improve our convergence. Suffice to say that there's a little bit more to the story, and you've seen it now. On to our final topic, that there always seems to be a lot of confusion, and I guess this is a little bit confusing. However, it's even more confusing if we don't use it. So here's a high-level block diagram, skipping some details, of our finite difference time domain algorithm, and it's all done on a Yee grid. So this 2x grid, we will temporarily create a slightly higher resolution grid, do some things, assign our devices, but then we're going to come away with just our permittivity and permeability distributed across our standard Yee grid, and the whole 2x grid thing is gone. The big mistake a lot of folks make is down in their code they start using parameters from this 2x grid that we just used to build the device. Once that's done, we throw out anything about a 2x grid, and from here down it's just as we've been learning in this class. So this is just a trick to figure out and sort out how to assign material properties to the grid. So I'll say this one more time because it's really important. Once we're done this step and we're calculating source, initializing FDTD in the main loop, all things 2x grid are gone. Don't ever do anything 2x grid down here. It's only a trick for building your device on the grid. Okay, our fields are staggered. Our epsilon xx exists at points where the ex exists. The epsilon yy exists where the y components of the electric fields exist. And the epsilon zz exists at the point where the z component of the electric field exists. And they're staggered. So in fact, even though we're within the same cell, the xx, yy, and zc elements of our permittivity array can be different. If there's a sort of a curved surface slicing through the middle of a cell, all three can be different. So in fact, we don't just come away with one array describing our permittivity. For 2 dimensions, assuming we're ignoring all the off-diagonal tensor elements, we need 3. An epsilon xx, an epsilon yy, and an epsilon zz. And if there's something going on with the magnetic response, we potentially need 3 more. A mu xx, a mu yy, and a mu zz. So, and they all exist at different points in the grid. So we have this really confusing problem of there's only one device, it's only in one position, but we have to figure out which components are inside and outside, and that can get very difficult. So here's a device, and here's that device overlaid onto a 1x grid, and these little dots here, I'm showing where the field components lie. We'll get into more detail here, but we can see even within one cell, take this cell, there's a green dot inside this cylinder, and the blue and the red dot are essentially outside. So we're already going to be assigning different material properties even within one cell. So it's getting very confusing. And when we're done, we end up with 3 different arrays. And see how crazy this is. How do we sort this out? That is the utility of this 2x grid, because this is a very difficult step if we don't do anything. So what's the alternative? Let's not go straight here. Let's go from our 1x grid. Let's calculate a grid with twice the resolution, twice as many points, but still representing the same physical amount of space. Then forget everything about a Yee grid. Just build our device, one device on one grid. And then once we have that, we just pick the material properties off to form these 1D arrays. And you'll see it's one line of MATLAB code for each of these arrays that we need. And so all of these steps are in fact very easy. Going straight from here to the device on the 1x grid, that's very difficult. But instead we go in easier steps this way by using this thing called a 2x grid. All right, so let's back up and talk about this from the beginning again. The Yee grid, we have staggered our field components, and we did this for a number of reasons. It's much more elegant for our finite difference equations. It implicitly satisfies the divergence equations, so we don't have to worry about those. And our physical boundary conditions are naturally satisfied. So if we have a material interface, everything works out. So this Yee grid works out really, really well. We also said that we will define our relative permittivity terms, epsilon xx, to be at the same points as the x component of the electric field. Epsilon yy will be where ey exists. Epsilon zz will be where ez exists. So our epsilon xx's will be defined at these points within the cell. Epsilon yy will be defined at these points, and epsilon zz at these points. And we do a similar thing with the permeability. Mu xx exists where hx exists. That's up here. And so on. So we're placing our tensor elements with the fields in this manner. So they're staggered, and if we have a material interface sliced through the middle of the cell, they can potentially be different. So we're coming away with 6 arrays, 3 for the permittivities and 3 for the permeabilities. Let's look at our two-dimensional grid for the E mode. And for the E mode, we see if we look at one of the cells right here, we see we have an electric field at the origin of that cell. We have our X component of the magnetic field right here, offset halfway down the y-axis. And then the Y component of the field offset halfway down the x-axis through the cell. And so this arrangement of 3 fields for our EZ mode, it repeats itself through all the cells. So what I want to do, rather than keep drawing 3 dimensions, I want to draw this as a 2-dimensional figure. So here's a little legend of how this works. We see the X component of the magnetic field, our Y component of the magnetic field, and the Z component of the electric field. And where they're located, roughly within one of the Yee cells, and then that pattern repeats itself. So this is our 1x grid and how the fields distribute themselves, and the notation that we'll be using for these. Notice, because of the way these fields are arranged, it's kind of like we're getting twice the resolution that we would be, because they're staggered. So let's go ahead and do that. Within one cell, let's put dashed lines going through this, dividing this one cell into 4 little cells. And we still keep the same alignment with the fields and everything else. So now we're looking at all these little cells. We have a new grid with twice as many cells in it, but still representing the same physical amount of space. We call this the 2x grid. And so what we'll do then, once we have this 2x grid, which simply has twice as many points as the 1x grid, we will build our device on that. So we just have one 2x grid. We will build our device on it, and then parse that out over to the 1x grid. So here's our original 1x grid, just 4x4, and so a cylinder that we wanted to put on this. So we build our 2x grid, and now we put our cylinder on the 2x grid. This clearly is going to look a little bit better because we have twice as many points. So let's go ahead and do that. We put that cylinder onto our 2x grid. And also remember from our previous discussion, there's really 2 ways we could do that. We could do a simple binary threshold where we're doing a staircase approximation, or we could do smoothing onto the 2x grid and maybe get a little bit better representation. So the easiest is just a staircase, and that still works pretty well, but if you want to get fancier, you can also blur it. So now we have our device built onto this 2x grid. And in doing this, building on the 2x grid, we don't even think yet anything about Yee Grid. We just calculate our grid resolution, create a whole other grid that has twice as many points, and build our device on it. Now we want to start figuring out how this relates back to our original 1x grid. So I have the dashed lines where we've divided our 1x grid cells. The 1x grid is our original Yee grid. So I'm outlining now one cell from the original Yee grid that we've divided into 2x2 cells. And here's the device that we were modeling, some kind of cylinder, and we can see where the materials lie. And so we can see there are some cells, for example, this cell. 2 of the points lie within the dielectric, and 2 of the points do not. So this gives us some hints in how we're going to populate our ultimate arrays. So here goes. Here's where we are and how the field components lie. What we'll do to calculate epsilon ZZ, these exist where the EZ components exist. Remember, the EZ components are the blue circles here. So there's an EZ here, there's an EZ here, an EZ here, and an EZ here. None of those are in dielectric. So notice the whole first row is not in dielectric. Then we go to the second row. No dielectric, 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 dielectric. So up here we just fill in the entire cell, no dielectric, 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 dielectric. Then we get down to the third row. No dielectric, 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 dielectric. So no dielectric, 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 dielectric. And we do this for all the rows. No dielectric, 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 no dielectric. So we fill in no dielectric, 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 no dielectric. Then we'll move here. Here's the permeability, mu sub xx, which exists everywhere h sub x exists. So it's the green arrows. So we read off these points. No dielectric, 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 no dielectric. So that's how we fill in our top row. No dielectric, 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 no dielectric. And we do a similar thing. We go row by row, and we're pulling off essentially every other cell from our 2x grid and populating our 1x grid. And it turns out each one of these arrows is just one line of code in MATLAB. Very easy in MATLAB. But we have this original device built on the 2x grid, one line of code to build URYY from this 2x grid, one line of MATLAB code to build ERZZ from the 2x grid, and another single line of code to build URXX from the 2x grid. Let's look at that code. So we'll focus in on this middle row. Here's the Yee cell for our EZ mode. And here's our 3 lines of code for generating ERZZ, URXX, URYY, as we saw them on the previous slide. So notice these arguments, they start somewhere, they skip every other cell and go to the end. Start somewhere, skip every other cell, and go to the end. So in fact, the input arguments are the same except for this first starting point. And we have to figure out where they need to start. So think about the x direction for ERZZ. So we're filling in the x direction for EZZ. Well, notice it's at the very beginning. It's not offset down the cell at all. So we start at a 1. In the y direction, same thing. It starts at the beginning. It's not offset by a half cell. So it also starts at 1. Let's think about URXX. So we're talking about the permeability associated with HX, so it exists at this point. So what do we do in terms of the x direction? The x direction is this direction. It starts at the very beginning of the cell, so we start at 1. And of course go every other cell to the end. Now what about in the y direction? Here it's offset a half cell. So in this case, on the 2x grid, we start at position 2, but we still go every other cell and go to the end. So that's how we think through this. And if we have a fully three-dimensional grid, here's how we do the parsing. And if we had the H mode, here's how we do the parsing. But you'll notice both of these sets of equations are really just special cases of the fully three-dimensional case. So one line of MATLAB code to pull off from the 2x grid to the 1x grid. Notice we have this ER2. That's my notation for the permittivity on the 2x grid. That then we parse off and get an ERZZ, or potentially ERXX and ERYY. Maybe we're interested in both modes. Likewise, we have a UR2. That's the permeability on a 2x grid. And we can parse off the XX, YY, and even the ZZ components from that, all from the same UR2. Now for the fully anisotropic case, which we're not really talking about a whole lot, but there are some things I can point out. In our permittivity tensor, the entire first column, we will define all of those to exist at the same point as EX. Second column, we define all those to exist at the same point as EY, and the third column to exist all at the same points as EZ. And a similar thing for the permeability. The first column exists at the same point as HX, second column exists at the same point as HY, and everything in the third column exists at the same points as HZ. So if we're actually modeling something anisotropic, we actually need to build 9 or even 18 different three-dimensional arrays on a 2x grid. So we'll have an ER2XX on a three-dimensional grid, an ER2XY on a three-dimensional grid. But here's how we parse them to get our tensor elements on the 1X grid. So clearly there's a lot more work, a lot more memory and stuff like that that has to happen here. We won't do that in this class, but I wanted you to see this.